Hello, friends. Albert Einstein was a famous scientist who changed the way we see the world and the universe. Physics principles have taken humanity a long way, and it's not just for our species. The cool thing about science is that with scientific thinking, one person can achieve a lot in their life. It's like knowing the rules of a game. If you know them, you'll play better. Also, remember that this means we can make our lives and the lives of those around us better. That's why I've brought you this video series to help you understand the universe, the world, and life deeply. If you watch it till the end, you'll have knowledge like someone who graduated from a physics university. I know you don't just want theories, you want to know things and improve your life with this knowledge. So, get ready, because people will start calling you a genius after this series. Let's start exploring the universe together. The story begins in 1831 in England's Royal Society, where a young genius named James Clerk Maxwell was born in Scotland. Maxwell was exceptional. He presented his first research paper to the Royal Society at just 14 years old. By 16, he was in college, and at 19, he had graduated. He loved math and geometry and spent a lot of time on his research. Even though his parents advised him differently, Maxwell was so passionate about math and geometry that he didn't listen to them. Little did his parents know that their son would go on to solve a significant scientific problem. Maxwell was born 12 years before an important concept in electromagnetism, discovered by Michael Faraday. However, Faraday didn't have a formal education and couldn't explain his ideas easily. So, in 1855, Maxwell presented a research paper that used a new mathematical language called vector calculus to explain Faraday's ideas. This new language helped make Faraday's concepts clearer and more understandable. Maxwell's equations are a set of 4 famous equations that explain everything about how electricity and magnetism work together. They are crucial in understanding how things like electricity, magnets, and even light function. Before Maxwell's work, people thought that electric and magnetic fields were just imaginary concepts. But Maxwell's equations showed that these fields are real and have energy and momentum. One key idea from Maxwell is that light is like a wave that travels at a constant speed, but this speed depends on how fast you are moving relative to the light. Imagine you are on a moving train and you throw a stone. The speed of the stone will be more than the speed of the train. But if you turn on a flashlight inside the train, the light coming out of it always travels at the same speed, no matter how fast the train is moving. Maxwell's equations challenged the old idea that motion was always relative and changed how we understand the universe. They are a fundamental part of physics and have had a big impact on our technology and our view of the world. In the 19th century, physicists believed in the existence of an absolute frame of reference called the ether. This ether was thought to be an invisible medium that filled the entire universe, and it was believed to be necessary for the propagation of light. Without this ether, it was thought that we wouldn't be able to see anything, just like we can't hear anything in the absence of air in space. Maxwell's equations had shown that light was a wave, with electric and magnetic fields vibrating in the ether. However, there was a problem. Water waves, for example, require a surface, but light seemed to propagate through the entire space. So, what exactly was this mysterious ether, and how could it support light waves? The ether theory also introduced the idea of relative motion. The motion of objects depended on their motion relative to the ether frame. It was believed that just as a moving train changes the pitch of its sound when it approaches or moves away from you, light should also show similar effects due to its relative motion with the ether. To test the existence of the ether, the famous Michelson-Morley experiment was conducted. They used a clever setup involving mirrors and light interference. If Earth moved through the ether, the speed of light should vary when measured in different directions. Surprisingly, they found no evidence of such variation. Some physicists, like H.A. Lorentz, proposed that the ether's motion might cause a contraction of objects in motion, which could explain the null result of the Michelson-Morley experiment. This idea introduced the concept of Lorentz length contraction. However, Albert Einstein turned things upside down with his special theory of relativity. He said, "Forget about the ether. Let's build a theory that works without it." That's when the magic happened. He proposed that the speed of light is constant for all observers, regardless of their motion. This revolutionary idea led to the development of his Special Theory of Relativity. Special relativity brought us some mind-boggling concepts like length contraction and time dilation. Imagine a world where moving objects shrink in size and time itself slows down as they approach the speed of light. These ideas were groundbreaking, challenging our everyday perceptions of the universe. In Einstein's world, some crazy things happen when you travel super fast, like close to the speed of light. Objects start to shrink and time slows down. Imagine your car getting shorter as it speeds up. Mind-blowing, right? But the fun doesn't stop there. We've got the famous twin paradox. Imagine two twins. One stays on Earth, and the other zooms off in a spaceship. When the space twin returns, they're younger than their Earth twin. Crazy, right? We'll explain why. Einstein also taught us that what's simultaneous in one place might not be in another. Think of it like turning on two light bulbs in a moving train. It's all about perspective. Einstein told us there's a speed limit in the universe. Nothing can go faster than light. Now, back to the twin paradox. The secret is acceleration. When you speed up or slow down, time gets wonky. So, the space twin aged less because of their spaceship's accelerations. It's like a cosmic time trick. Let's go way back to the 1600s when Isaac Newton was rocking the world. He came up with a simple idea. Everything in the universe happens in two things, space and time. It's like the stage and the timeline for everything. Then fast forward to the 1900s, and here comes Einstein. He had a big revelation called special relativity. It's like he said, "Hey, space and time aren't as simple as we thought." Einstein introduced this cool concept called spacetime. It's like a new kind of stage where space and time blend together. Imagine it as the canvas for everything in the universe. Special relativity isn't just about space and time. It connects with a bunch of other things like energy, mass, and even quantum physics. It's like a puzzle piece that fits into many parts of science. Special relativity and quantum physics teamed up to create something called quantum field theory. It's like the ultimate calculator for tiny particles and can make predictions super precisely. One of the coolest things special relativity did was to show that electricity and magnetism are like two sides of the same coin. They're just different views of something called the electromagnetic field. And you know that famous equation, E equals to mc squared. It says that energy and mass are connected. It's not about turning one into the other. It's more like they're two forms of the same thing, kind of like ice and water. So there you have it. Newton and Einstein shook up our understanding of the universe. But guess what? Our journey isn't over yet. In the next video, we'll dive into Einstein's most famous theory, one that helps us understand the mysteries of space. Stay tuned. Thanks for hanging out with us today. Don't forget to like, subscribe, and hit that bell to catch our next adventure into the awesome world of science. Until then, keep wondering and exploring the universe.